A lepton is an elementary, half-integer spin particle that does not undergo strong interactions, but is subject to the Pauli exclusion principle. The best known of all leptons is the electron, which is directly tied to all chemical properties. Two main classes of leptons exist, charged leptons, and neutral leptons. Charged leptons can combine with other particles to form various composite particles such as atoms and positronium, while neutrinos rarely interact with anything, and are consequently rarely observed. There are 6 types of leptons, known as flavours, forming 3 generations. The first generation is the electronic leptons, comprising the electron and electron neutrino, I1/2, E. The second is the muonic leptons, comprising the muon and muon neutrino, I1/2, I1/4. And the third is the tauonic leptons, comprising the tau and the tau neutrino, I1/2, I. Electrons have the least mass of all the charged leptons. The heavier muons and taus will rapidly change into electrons through a process of particle decay, the transformation from a higher mass state to a lower mass state. Thus electrons are stable and the most common charged lepton in the universe, whereas muons and taus can only be produced in high-energy collisions. Leptons have various intrinsic properties, including electric charge, spin, and mass. Unlike quarks, however, leptons are not subject to the strong interaction, but they are subject to the other 3 fundamental interactions: gravitation, electromagnetism, and the weak interaction. For every lepton flavor there is a corresponding type of antiparticle, known as antilepton, that differs from the lepton only in that some of its properties have equal magnitude but opposite sign. However, according to certain theories, neutrinos may be their own antiparticle, but it is not currently known whether this is the case or not. The first charged lepton, the electron, was theorized in the mid-19th century by several scientists and was discovered in 1897 by J. Thomson. The next lepton to be observed was the muon, discovered by Carl D. Anderson in 1936, which was classified as a meson at the time. After investigation, it was realized that the muon did not have the expected properties of a meson, but rather behaved like an electron, only with higher mass. It took until 1947 for the concept of leptons as a family of particle to be proposed. The first neutrino, the electron neutrino, was proposed by Wolfgang Pauli in 1930 to explain certain characteristics of beta decay. It was first observed in the Kowane-Raines neutrino experiment conducted by Clyde Cowan and Frederick Raines in 1956. The muon neutrino was discovered in 1962 by Leon M. Lederman, Melvin Schwartz and Jack Steinberger, and the tau discovered between 1974 and 1977 by Martin Lewis Pearl and his colleagues from the Stanford Linear Accelerator Center and Lawrence Berkeley National Laboratory. The tau neutrino remained elusive until July 2000, when the Donut collaboration from Fermilab announced its discovery. Leptons are an important part of the Standard Model. Electrons are one of the components of atoms, alongside protons and neutrons. Exotic atoms with muons and taus instead of electrons can also be synthesized, as well as lepton-antilepton particles such as positronium. Etymology: the name lepton comes from the Greek micron I leptocubed s, fine, small, thin. The earliest attested form of the word is the Mycenaean Greek th €10 mu, repotu, written in Linear B syllabic script. Lepton was first used by physicist La Copyright on Rosenfeld in 1948. Following a suggestion of Professor C. Marlaire, I adopt a as a pendant to nucleon the denomination lepton to denote a particle of small mass. The etymology incorrectly implies that all the leptons are of small mass. When Rosenfeld named them, the only known leptons were electrons and muons, which are in fact of small mass the mass of an electron and the mass of a muon are fractions of the mass of the heavy proton. However, the mass of the tau is nearly twice that of the proton, and about 3,500 times that of the electron. History: the first lepton identified was the electron, discovered by J. Thomson and his team of British physicists in 1897. Then in 1930 Wolfgang Pauli postulated the electron neutrino to preserve conservation of energy, conservation of momentum, and conservation of angular momentum in beta decay. Pauli theorized that an undetected particle was carrying away the difference between the energy, momentum, and angular momentum of the initial and observed final particles. The electron neutrino was simply called the neutrino, as it was not yet known that neutrinos came in different flavors. Nearly 40 years after the discovery of the electron, the muon was discovered by Carl D. Anderson in 1936. Due to its mass, it was initially categorized as a meson rather than a lepton. It later became clear that the muon was much more similar to the electron than to mesons, as muons do not undergo this strong interaction, and thus the muon was reclassified. Electrons, muons, and the neutrino were grouped into a new group of particles, the leptons. In 1962 Leon M. Lederman, Melvin Schwartz and Jack Steinberger showed that more than one type of neutrino exists by first detecting interactions of the muon neutrino, which earned them the 1988 Nobel Prize, although by then the different flavors of neutrino had already been theorized. The tau was first detected in a series of experiments between 1974 and 1977 by Martin Lewis Pearl with his colleagues at the SLACLBL group. Like the electron and the muon, it too was expected to have an associated neutrino. The first evidence for tau neutrinos come from the observation of missing energy and momentum in tau decay, analogous to the missing energy and momentum in beta decay leading to the discovery of the electron neutrino. The first detection of tau neutrino interactions was announced in 2000 by the Donut collaboration at Fermilab, making it the latest particle of the Standard Model to have been directly observed, apart from the Higgs boson, which probably has been discovered in 2012. Although all present data is consistent with 3 generations of leptons, some particle physicists are searching for a 4th generation. The current lower limit on the mass of such a 4th charged lepton is 700210080000000 unregistered trademark 100.8 GeV-C2, while its associated neutrino would have a mass of at least 7001450000000 unregistered trademark 45.0 GeV-C2. Properties equals spin and chirality equals. Leptons are spin 1 or 2 particles. The spin statistics theorem thus implies that they are fermions and thus that they are subject to the Pauli exclusion principle. No 2 leptons of the same species can be in exactly the same state at the same time. Furthermore, it means that a lepton can have only 2 possible spin states, namely up or down. A closely related property is chirality, which in turn is closely related to a more easily visualized property called helicity. The helicity of a particle is the direction of his spin relative to its momentum. Particles with spin in the same direction as their momentum are called right-handed and otherwise they are called left-handed. When a particle is massless, the direction of its momentum relative to its spin is frame-independent, while for massive particles it is possible to overtake the particle by a Lorentz transformation flipping the helicity. Chirality is a technical property that agrees with helicity for massless particles and is still well-defined for massive particles. In many quantum field theories such as quantum electrodynamics and quantum chromodynamics left and right-handed fermions are identical. However, in the Standard Model left-handed and right-handed fermions are treated asymmetrically. Only left-handed fermions participate in the weak interaction, while there are no right-handed neutrinos. This is an example of parity violation. In the literature, left-handed fields are often denoted by a capital L subscript and right-handed fields are denoted by a capital A subscript. Electromagnetic interaction equals. One of the most prominent properties of leptons is their electric charge, Q. The electric charge determines the strength of their electromagnetic interactions. It determines the strength of the electric field generated by the particle and how strongly the particle reacts to an external electric or magnetic field. Each generation contains 1 lepton with Q equals AE and 1 lepton with 0 electric charge. The lepton with electric charge is commonly simply referred to as a charged lepton while the neutral lepton is called a neutrino. For example, the first generation consists of the electron A with a negative electric charge and the electrically neutral electron neutrino I1/2, E. In the language of quantum field theory, the electromagnetic interaction of the charged leptons is expressed by the fact that the particles interact with the quantum of the electromagnetic field, the photon. The Feynman diagram of the electron-photon interaction is shown on the right. Because leptons possess an intrinsic rotation in the form of their spin, charged leptons generate a magnetic field. The size of their magnetic dipole moment I1/4 is given by where m is the mass of the lepton and g is the so-called g factor for the lepton. First-order approximation quantum mechanics predicts that the g factor is 2 for all leptons. However, higher-order quantum effects caused by loops in Feynman diagrams introduce corrections to this value. These corrections, referred to as the anomalous magnetic dipole moment, are very sensitive to the details of a quantum field theory model and thus provide the opportunity for precision tests of the standard model. The theoretical and measured values for the electron anomalous magnetic dipole moment are within agreement within 8 significant figures. Weak interaction equals, in the standard model the left-handed charged lepton and the left-handed neutrino are arranged in doublet, I1/2, L, Al, that transforms in the spinor representation of the weak isospin SU, gauge symmetry. This means that these particles are eigenstates of the isospin projection T3 with eigenvalues 1/2 and 1/2 respectively. In the meantime, the right-handed charged lepton transforms as a weak isospin scalar and thus does not participate in the weak interaction, while there is no right-handed neutrino at all. The Higgs mechanism recombines the gauge fields of the weak isospin SU, and the weak hypercharge U, symmetries to 3 massive vector bosons mediating the weak interaction, and 1 massless vector boson, the photon, responsible for the electromagnetic interaction. The electric charge Q can be calculated from the isospin projection T3 and weak hypercharge YW through the Gell-Mann-Nishijima formula. Q equals T3 plus YW/2, to recover the observed electric charges for all particles. The left-handed weak isospin doublet, I1/2, L, Al, must thus have YW equals a 1, while the right-handed isospin scalar A, R must have YW equals a 2. The interaction of the leptons with the massive weak interaction vector bosons is shown in the figure on the left. Mass equals. In the standard model each lepton starts out with no intrinsic mass. The charged leptons obtain an effective mass through interaction with the Higgs field, but the neutrinos remain massless. For technical reasons the masslessness of the neutrinos implies that there is no mixing of the different generations of charged leptons as there is for quarks. This is in close agreement with current experimental observations. However, it is known from experiments most prominently from observed neutrino oscillations that neutrinos do in fact have some very small mass, probably less than 700020000000000 unregistered trademark 2 EVC2. This implies the existence of physics beyond the standard model. The currently most favored extension is the so-called seesaw mechanism, which would explain both why the left-handed neutrinos are so light compared to the corresponding charged leptons, and why we have not yet seen any right-handed neutrinos. Leptonic numbers equals. The members of each generation's weak isospin doublet are assigned leptonic numbers that are conserved under the standard model. Electrons and electron neutrinos have an electronic number of Le equals 1, while muons and muon neutrinos have a muonic number of Le 1/4 equals 1, while tau particles and tau neutrinos have a tauonic number of Le equals 1. The anti-leptons have their respective generations' leptonic numbers of a 1. Conservation of the leptonic numbers means that the number of leptons of the same type remains the same when particles interact. This implies that leptons and anti-leptons must be created in pairs of a single generation. For example, the following processes are allowed under conservation of leptonic numbers. A plus E plus AI cubed plus I cubed, IA plus I plus a ZO plus ZO, but not these, I cubed A plus I 1/4 plus, Y A plus I 1/2, I, ZO AI 1/4 A plus I plus. However, neutrino oscillations are known to violate the conservation of the individual leptonic numbers. Such a violation is considered to be smoking gun evidence for physics beyond the standard model. A much stronger conservation law is the conservation of the total number of leptons, conserved even in the case of neutrino oscillations, but even it is still violated by a tiny amount by the chiral anomaly. Universality: the coupling of the leptons to gauge bosons are flavor independent. This property is called lepton universality and has been tested in measurements of the tau and muon lifetimes and of Z boson partial decay widths, particularly at the Stanford Linear Collider and Large Electron Positron Collider experiments. The decay rate of muons through the process I1/4 AAA plus I1/2, E plus I1/2, I1/4 is approximately given by an expression of the form where K1 is some constant, and GF is the Fermi coupling constant. The decay rate of tau particles through the process IAAA plus I1/2, E plus I1/2, I is given by an expression of the same form where K2 is some constant. Mer-only-Eurotorn universality implies that K1 equals K2. On the other hand, electron-Euromuon universality implies. This explains why the branching ratios for the electronic mode and muonic mode of tau decay are equal. Universality also accounts for the ratio of muon and tau lifetimes. The lifetime of a lepton is related to the decay rate by where B, XAY, and I, XAY, denotes the branching ratios and the resonance width of the process XAY. The ratio of tau and muon lifetime is thus given by using the values of the 2008 Review of Particle Physics for the branching ratios of muons and tau yields a lifetime ratio of 699312900000000 unregistered trademark 1.29a, 10(7), comparable to the measured lifetime ratio of 69931319999999999 unregistered trademark 1.32a, 10(7). The difference is due to K1 and K2 not actually being constants. They depend on the mass of leptons. Table of leptons. See also, Coid formula, list of particles, prions are hypothetical particles which were once postulated to be subcomponents of quarks and leptons. Notes. References: see Amsler al. Amsler. Dosa. Antonelli. Osner. Babu. Bear. Band. Barnett. Berggren. Beringer. Bernardi. Beryl. Beixel. Bebel. Bloch. Blucher. Blusk. Kahn. Kariner. Kazo. Sechuchsi. Chakraborty. Chen. Chivakula. Cowan. Dahl. D'Ambrosio. Damer al. Review of Particle Physics. Physics Letters B667, 1. Bibcode, 2008 PHLB 667, 1 P. doi, 10.1016/J. Physlip. 2008.07.018. IV Anisin. The neutrino its past, present and future. SFIN Year 15, Series A, Conferences, No. A23 59, 3172. AR Ziv, Physics/05031172. Bibcode, 2005 Physics. 3172A. Y. Fukuda. Hayakawa, T. Ichihara, E. Inu, K. Ishara, K. Ishino, H. Ito, Y. Kajita, T. al. Evidence for oscillation of atmospheric neutrinos. Physical Review Letters 81, 1562 1567. AR Ziv, Hepex/9807003. Bibcode, 1998 PHRVL 81.1562 F. doi, 10.1103/Phys Rev Let 81.1562. CS1 Maintenance, Explicit Use of AL. K. Kodama. Ashida, N. Andriopoulos, C. Solido, N. Xenakos. G. Jaeger, P. Baller, B. Bainlein, D. Freeman, W. Lundberg, B. Morfin, J. Raymaker, R. Yun, J.C. Song, J.S. Yoon, C.S. Chung, S.H. Burfors, P. Kbontsev, M. Ray, N.W. Sidgwell, R. Stanton, N. Yoshida, S. Aoki, S. Hara, T. Ri, J.T. Sayampa, D. Erickson, C. Graham, M. Heller, K.A.L. Observation of tau neutrino interactions. Physics Letters B504, 218. A.R. Ziv, HEPEX/001235. Bibcode, 2001 PHLB 504 218 D doi, 10.1016 per second 0370-2693, 01, 00307-0. B. R. Martin, G. Shaw. Chapter 2 Leptons, Quarks and Hadrons. Particle Physics. John Wiley and Sons, pages 23 47. ISBN 0-471-92358-3. S. H. Niedermeyer, C. D. Anderson. Anderson. Note on the Nature of Cosmic Ray Particles. Physical Review 51, 884 886. Bibcode, 1937 PHRV. 51884 Endoi, 10.1103/Phys Rev 51.884. J. Peltoniemi, J. Sarcamo. Laboratory Measurements and Limits for Neutrino Properties. The Ultimate Neutrino Page. Retrieved November 7, 2008. M. L. Pearl. Abrams, G. Boyarsky, A. Briedenbach, M. Briggs, D. Bellows, F. Chinosky, W. Darkine, J. A. L. Evidence for anomalous lepton production in E+A annihilation. Physical Review Letters 35, 1489 1492. Bibcode, 1975 PHRVL 35.1489 P doi, 10.1103/Phys Rev Let 35.1489. CS1 Maintenance, Explicit Use of AL. M. E. Peskin, D. V. Schroeder. Introduction to Quantum Field Theory. Westview Press. ISBN 0-201-50397-2. K. Reyes-Elman. Logbook, Neutrino Invention. Symmetry Magazine 4. L. Rosenfeld. Nuclear Forces. Interscience Publishers. P. XVII. R. Shankar. Chapter 2 Rotational Invariance and Angular Momentum. Principles of Quantum Mechanics. Springer pages 305 352. ISBN 978-0-306-44790-7. S. Weinberg. The Discovery of Subatomic Particles. Cambridge University Press. ISBN 0-521-82351-X. R. Wilson. Astronomy Through the Ages, The Story of the Human Attempt to Understand the Universe. CRC Press. Pages 138. ISBN 0-7484-0748-0. External links, Particle Data Group homepage. The PDG compiles authoritative information on particle properties. Leptons, a summary of leptons from hyperphysics.